So yesterday what we have learned is basically the usage of the equipments, okay, the lab equipments basically. Say your regulated power supply, your function generator, and then the digital storage oscilloscope. Today we will start with few of the experiments. So the first experiment that we will be doing is rectifier, then the filter, followed by the regulator. Before that, let's learn the fundamentals of the diodes, how it works. Okay, and a rectifier is nothing but an application of your PN junction diode. So let's start with the fundamental concepts, learn how the diode works, and then we'll go ahead with the experiments. Okay. So semiconductors, what do I mean by semiconductors basically? Pardon? What are semiconductors? How are the materials classified basically? Conductors, semiconductors, and then insulators. Okay, so basically the materials, if you take, they are classified into three. You have your conductors, semiconductors, and then your insulators. So conductors, what are they? Which allow your electrons to pass through or your electricity to flow through. Example is, classic example is copper. And insulators, if you come to insulators, it does not allow your current to pass through. So example is plastic, wood, and all that. And semiconductors are the one, it's going to be partially. So partially in the sense, how do you say it is partially? It acts as like a conductor, it acts like an insulator. So till we give certain voltage, right, it's going to be in the non-conducting state. Beyond that, it will start conducting. So they come under the category of what is called as your semiconductor, right? The examples, the classic examples for your semiconductor materials are silicon and germanium. Okay, so here silicon and your germanium are the classic examples. Now once again, if you take this semiconductor, there are two other categories. One we call it as the extrinsic and other is your intrinsic. What is intrinsic first of all? What is the difference between this intrinsic and extrinsic? I think many of you are from electronics background, so you should be knowing it. No, I'm just asking what is intrinsic and what is extrinsic? Pure form. Pure form. Which is pure form? Intrinsic. So intrinsic are nothing but the pure form of your semiconductors. Whereas extrinsic in the sense, we add impurities to it. Okay. So this is pure semiconductors. Extrinsic means the impurities are added to your semiconductors. Now, why do I have to add these impurities? Why do I have to add these impurities? I have a material, it is in a pure form. Why do I add impurity to it? In order to make it conductive. Okay, to make it conductive, we add what are called as the impurities. Those impurities, they are called as the dopants, and the process is called as doping. Okay, I think you would have heard these terms. Doping, and the impurities are called as the dopants. So process of adding impurities, doping. The impurities that are added are called as the dopants. So I have the semiconductor materials in the pure form. But in the pure form, what happens? The number of charge carriers will be the same. So as a result, the net current will be equal to 0. So it's useless. So what do? I go for the adding of impurities to my pure semiconductor. Because of what I arrive at what is called as the extrinsic semiconductor. Okay, so the process of adding impurities is called as doping, and the impurities that are added are called as the dopants, right? So this is the main thing. Now dopants, if you take, once again, it's classified as, the dopants can be trivalent or the pentavalent. It can be trivalent or it can be pentavalent compounds. So trivalent, what are all the examples? What are the trivalent impurities that I can add it to my silicon or my germanium? Phosphorus is a pentavalent compound. Okay, so phosphorus, okay, fine, it's an impurity, but pardon? Somebody gave some answer. Aluminium. So the trivalent aluminium, I can also say indium. Always we say whichever ends with IUM, they come under the trivalent category. So I can have aluminium, indium, gallium, boron, all are nothing but my trivalent. Phosphorus is a classic example of a pentavalent compound. Okay. So now this silicon, anybody who knows the atomic number of the silicon compound? 14. It's going to be 14. So silicon, if I take, the atomic number is 14, right? And how many electrons will be there in the outermost shell? 4. It will have 4 electrons in its outermost shell. So I'll have the compound in this fashion. You would have seen in your books where silicon will be given like this. I'll have the 4 electrons. What are those electrons called as? The electrons that are there in the outermost shell? They are called as valence electrons. Okay, they are whatever is there in the outermost shell, they are called as the valence electrons. I'm not going deep into it. Hope all of you know how that number 4 has come, because it's your basic physics. Fine. So 4 electrons are there in the outermost shell. So these electrons are nothing but your valence electrons. So basically your silicon compound, if you take, what happens? It has 4 electrons or 4 valence electrons. Now for this 4 electrons only, for this silicon compound only, we are adding this trivalent or the pentavalent impurity, and we are trying to make it as an extrinsic semiconductor so that the conductivity can be enhanced. Okay, clear till this? Basics of semiconductor, why do you have to go for doping, right? And what are the type of dopants that can be added? Now, if I try, let's say I have the silicon compound, I am trying to add a pentavalent compound to it. So what happens there? Let's see with the next diagram. So you have, let's say, pentavalent impurity is going to be added. So I have my silicon structure in this fashion, right? I have a silicon compound. where it has got 4 valence electrons. To this, say I am going to add a phosphorus as an impurity. So phosphorus, how many, we say it's a pentavalent. Pentavalent means how many valence electrons will be available for it? Penta means 5. It has got 5 valence electrons. So phosphorus will have 5 valence electrons. Out of 5, 4 is going to form a covalent bond with its nearest silicon atom. Right? So here also I'll have, say, silicon. So in my crystal lattice, I'll have my silicon atoms in this fashion. So 5 electrons are there. Out of 5, 4 forms the covalent bond with the nearby silicon atom. Now 1 electron out of this phosphorus, it's free. 1 electron, it's going to be free. That 1 electron is nothing but the conduction electron that will help us in our conduction. Okay, so if I add phosphorus as an impurity to my silicon, what do I get? I get an extra. What do I get? Extra electron. I get an extra electron over here. Okay, so if pentavalent impurities are added, I will have the electrons. Now, always when we say there are some positive, means we have something called as negative. If I say day, there is something called as night. So always I have a opposite for it. So when I say electron, electrons are nothing but negative charges. So when negative charges are there, there should be something called as the positive charge. What is that positive charge? Basically, holes. What is a hole? Is there anything physically that you have a hole? No. Hole is nothing but a vacancy created by an electron. Okay. Hole is nothing but a vacancy created by an electron is called as a hole. So if I say electrons are more, this is the negative charge. All of us know electrons means it's going to be the negative charge. So if negative charges are there, there should be something called as the positive charge. So what are those positive charges? The positive charges are nothing but my holes. Holes, it's not a physical. It's not a physical one. It is nothing but vacancy created by your electron. So if at all my electron here is dislocated, let's say it's dislocated, I give some potential, my electron gets dislocated and it is roaming here in the free lattice like this. This electron which is dislocated would have created what is called as a hole there. Okay, so hole is not a physical one, it is a virtual. Okay, the electron gets dislodged, the electron gets dislocated. As a result, there is a vacancy there. That vacancy is nothing but a hole, right? Now there is a hole, so electron from somewhere can come and fill this particular hole. So that's how the conduction takes place in your semiconductor basically. So now if I take, let us put it back to the same thing. So here, whenever I have a vacancy by electron, I get a hole created. Now what happens if I add this impurity? If I add this impurity, I will have lot of electrons in my lattice. Let's say there is a phosphorus here. Similarly, let's say I have a phosphorus compound over here, which forms a covalent bond with my nearby silicon. So like that, what happens? This phosphorus in turn will create one electron. So as such, if I see this particular diagram only, I have 2 electrons being created. So whenever I go for adding a pentavalent impurity, what happens? The number of electrons is going to be more. Okay, so that's why what do we say? If it is a pentavalent doping, the majority carriers are going to be electrons, and your minority carriers are going to be holes. Okay, so majority we call it as electrons because as such, if I dope it with phosphorus, I get more number of free electrons available. Okay, so the majority carriers are electrons, and your minority means less in number compared to the electron. So the minority carrier will be the holes. So holes, how do they get created? Whenever an electron gets dislodged, that empty space is nothing but a hole. We treat it to be a hole. That empty space created by the dislocation of the electron is nothing but a hole as such. So pentavalent impurity, if it is added in my semiconductor, then I will have more number of electron and less number of holes, which I term it as majority carrier and minority carrier, right? So this we have to keep in mind always. Pentavalent impurity, if it is added, my majority carriers are going to be electrons and my minority carriers are the holes. What do we call it as? By adding pentavalent, it results in what is called as an N-type semiconductor, because always we say PN junction, NPN transistor or PNP transistor, like that. So as I add this pentavalent impurity, it results in, or we get what is called as the N-type semiconductor. Okay, so because of addition of this, I end up in N-type semiconductor. Okay, so N means, you keep it in mind, N stands for negative. Negatives are nothing but the electrons. So in N-type, electrons will be more. If electrons are more, naturally the opposite charge is my hole, which will be less in number. Because all these concepts are something new for your students, right? So give them some shortcuts also such that they can remember. Clear? So you ask them to relate it in this fashion. What do I mean by N? N stands for your negative. So I have added a pentavalent impurity to it. So negative means my electron should be more. I'll have more number of electrons, which I call it as the majority carriers. So if electrons are majority, naturally my hole will be the minority carrier there. So what is minority? If it is less in number, we call it as minority. Okay, so this, how do we add this? In what proportion do we add this impurity? So 1 atom of phosphorus can be added to say 10 raised to 15 of your intrinsic. So you just imagine the proportion it's being added. I will add 1 atom of phosphorus to say 10 raised to 15 of my intrinsic silicon. So that's the rate in which I am going to add the impurities. So N-type, we have got an idea. Similarly, we need to know how do we arrive at the trivalent. So trivalent in the sense, how do we make it? Can you just help me out with that? So let's say I'm going to discuss about the trivalent, adding the trivalent impurity. So I have silicon. Silicon, as we know, there are 4 valence electron. Let's say I'm going to add the trivalent impurity, boron. So how many valence electron boron has? 3. So it goes like this. These are your covalent bonds. So boron will have 3 valence electron. So it has an electron here, here and here. So these 3, they form the covalent bond with my silicon. Whereas I have an empty space here. So what is that empty space? It means it can be filled with an electron. It is a vacancy there. Okay, it is a vacancy there which can be filled with an electron. So what is that called as? Hole. The vacancy of an electron is nothing but a hole. So I will have a hole here. I'll have a hole here because it is only a trivalent compound, so only 3 valence electrons are there, whereas my silicon is nothing but has 4 valence electrons. So one, it is short of forming the covalent bond. There is a vacancy here. So what does it mean? Somewhere from the crystal lattice, my electron can come and fill this place. Okay, so this is a vacant space which we call it as the hole. Right? So now what is the conclusion to be made if I add a trivalent impurity to my intrinsic semiconductor? Majority carriers are holes and your minority carriers will be the electrons. Okay. So if I add trivalent impurity, my majority carriers are holes and my minority is going to be electrons. Now, what is that type of semiconductor? How do we term that? It is called as a p-type. Okay. So, it is a p-type semiconductor. So, now what's the moral of the story? If I add a pentavalent impurity to my intrinsic semiconductor, I arrive at N-type. In N-type, the majority carriers are electrons and the minority are the holes. If I add a trivalent impurity to my intrinsic semiconductor, I arrive at P-type. Majority are holes and minority are going to be electrons. So clear with this? So this is the fundamental concept of forming my semiconductor material. Clear? Have you taken the diagram? No. Now what do? We go for the next one, what is called as our diode, our semiconductor device, which is nothing but my diode. Okay, so this is a semiconductor device. Clear? Now diode means how many terminals are there for this? 2 terminal. It's basically a 2-terminal device. And how is it formed? By combining my p-type and then my n-type semiconductors. Okay, I combine my p-type and then my n-type semiconductor and I arrive at what is called as my diode, a p-n junction diode. Now this has got 2 terminals. What are the terminals of the diode termed as? Anode and cathode. So anode is P side and cathode is your N side. See, always even in interviews we have seen people telling what are the terminals of the diode? Positive, negative. Please don't entertain that answer. Even if your students give that answer, please, it's wrong. It should be termed as anode and cathode. Right? So P side is my anode and N side is going to be my cathode. Right? Now what happens? Why do you basically call it as a diode? And it is going to allow your current flow in only in one direction. It will allow the current to flow only in one direction and it will offer a large resistance in the other direction. Right? Now, if you have seen your textbooks or the materials, you would have seen a diagram in this fashion where I will have say P side and then a N side. Now, in the P side, you would have seen a negative and then a hole. A negative, a hole. Okay. And in the N side, if you take, you would have seen a positive with an electron, positive with an electron, okay. And here I have what is called as my depletion region. So this depletion region will basically consist of this. We'll come to it. What exactly are they? Okay. So this region is called as my depletion region. So when do I have that? When I combine my both P and N type material, I have this structure where I have a depletion layer formed. How this depletion layer gets formed? It's because of, yes, attraction of. Basically, there is charge imbalance. Okay, here in P side you have lot of holes, whereas in N side you have lot of electrons. So what happens there? There is a charge imbalance. More positive charges on one side, more number of negative charges on the other side. So what happens? Positive will try to move towards the negative side, and from negative side it tries to move towards the positive side. So because of that, you have something created in between, which we call it as the depletion region. So now what is happening? A hole is moving. A hole is moving from the positive side, that is P side, to the N side. Right? A hole is moving from the P side to the N side, and an electron from the N side is moving towards the P side. So whenever an electron moves, what type of ion will get created? You had your phosphorus structure like this. I had my phosphorus. There was one free electron, right? That free electron is only shown in this fashion. Now when I combine both my P and N material, there is a charge imbalance existing. So what's happening? As there are more number of electrons this side, it tries to move from N side to the P side. Now similarly, there are more number of holes on the P side, so it tries to move from the P side to the N side. Till this, is it clear? Now my question is, we say the electron is moving from the N side to the P side. Whenever an electron has moved, what type of ion will get created? See, I have a phosphorus. There are 5 valence electrons. One electron has been moved. What type of ion will it become? It has lost one of its negative charge. I am giving all the clue. It becomes what is called as your positive ion. It is losing its negativity. Okay, so that's why in the diagram, how do we show? We show it as a positive ion there. Because the electron can be moved from the N side towards the P side. So when it loses one electron, it is basically losing its negative charge. When it loses its negative charge, it becomes a positive ion. Right? Now this electron is coming to the P side. There is a hole. So what happens? This electron goes and fills the hole. So what will happen to my boron there? I have a hole here. The electron comes and fills the hole. So what will happen to boron there? It is getting one more negative charge. Right? So what type of ion will it become? Negative ion. Clear? So that's why we show always on the P side the negative ion with a hole, and on the N side we will show the positive ion with an electron. Clear with this? So what's happening in N side? Phosphorus has got 5 electrons. There are more number of electrons. And on the P side, I have the boron impurity. It has got more number of holes as such. Now when I combine both my P and N type semiconductor, there is a charge imbalance existing other side. So what happens? They try to move in order to balance the number of charge carriers. So my holes will move from P to N, and electrons will move from N to P. So when I say my electron is moving from N to P, what happens there? This phosphorus ion, it is losing its negative charge. As it is losing its negative charge, it becomes what is called as a positive ion. Right? Now this electron goes and fills the holes that is there in my P side. Now what happens here on the P side? The boron, the negativity has increased. It has gained one electron. As a result, it becomes a negative ion. Clear? Now in between this, we have, because it has lost an electron, it has become a positive. This fellow has gained an electron, it has become a negative ion. So this region where you have only these ions present, it is called as the depletion region. The depletion region will not contain the electrons or the holes. It will contain only the immobile ions. Okay, my electron and hole are mobile particles, whereas my ions, positive and then the negative ion, are immobile by nature. Immobile by nature. So my depletion region, what gets formed because of this charge imbalance, electrons moving from N to P and holes moving from P to N, I have this region created which I call it as the depletion region. That depletion region is going to contain only my immobile ions. Clear? Only my electron and hole are going to be the mobile charge particles. These ions are going to be the immobile ones. Immobile means it cannot move. So now this is the depletion region, and to this only we associate what is called as the, we say silicon has a cut-in voltage of, what is the value? 0.7 ideally speaking, and germanium has a cut-in voltage of say 0.3. 0.3 ideally speaking. Okay, so we say silicon, the cut-in voltage is 0.7, and for germanium it's going to be 0.3 volt. So this is nothing but the barrier potential. What we are talking about is nothing but the barrier potential. So this is nothing but the depletion region, and it has got a potential which we call it as the barrier potential, and that barrier potential is only for silicon, it is 0.7 volt, and for germanium it is 0.3 volt, ideal values. Practically it might vary, okay, which we can observe when we are doing our experiments. So this barrier potential only, we say these are the theoretical values, and when I am providing a bias to it, it has to overcome this barrier potential. Clear? So here you can see positive on one side, negative on the other side. You have a field existing there. That is nothing but this 0.7 or the 0.3 volt depending upon my material. Clear? So first we saw about P, we saw about N. Now we have combined both N and P. You arrive at what is called as your semiconductor diodes. So if I combine both of them, what happens? There is a charge imbalance existing, because this P side has more holes, N side has more electrons. So in order to equalize the charge carriers, it will start moving from, say the holes will start moving from P to N. The electrons will start moving from N to P. As a result, I will have a barrier, and that barrier is nothing but termed as your depletion region, and the potential associated with that is called as your barrier potential, which we generally term it as 0.7 for your silicon and 0.3 for your germanium. And did you understand how the ions are being created? Right? So an electron is lost means negativity is less. So as a result, it becomes a positive ion. If it gains one electron, what happens? The negativity is increased. So it becomes a negative ion. Clear? So now this is at the outside. Now what are we going to do? This we are going to bias, and we arrive at what is called as the forward bias and then the reverse bias. How my diode is going to work in the forward bias condition as well as in the reverse bias condition, that we will see further. Okay. So diode, we say I'm going to forward bias and then the reverse bias. So I have my Tn. The barrier will be there. I'll have lot of holes. And this side I have the electrons. So I'll have the ions here, which is nothing but my depletion, right? To this, we give some potential. First of all, what is meant by biasing? We say forward bias, reverse bias, and all that. What do I mean by biasing? Applying voltage in order to make your device operative. Okay, so you apply some DC potential in order to make your device operative. That is nothing but your bias. Now, forward bias means, let's say I'm going to discuss about the forward bias. We say this is the anode and this is the cathode. Now, to the P, what am I going to connect? What terminal will I connect? Positive. And to the N? Negative. Okay, so this is what, let's say V, right? I'm going to connect in this fashion. So generally, when do we call it as forward bias? P2? P2? Anode is connected to positive. Then cathode is connected to negative. Is that the forward bias?
Anode to cathode, only in one direction.
No, that is the effect of giving the bias. Agreed. Electrons will start moving, all that will happen. But that's the effect of biasing. First, my question itself is, we got to know what is bias. You are applying some potential in order to make it operative, make your device operative. Now we are talking about something called as forward bias. So by the logic you are telling, my P type should be connected to positive and my N type should be connected to negative. My question is that the forward bias? No. So how do we have to term the forward biases? The anode will be at a higher positive potential compared to that of my cathode. Because this is not going to be the case all the time. P connected to, or say anode connected to positive and cathode connected to negative will not be the case all the time. So anode should be at a higher positive potential compared to that of my cathode. Okay, so that is how we have to define our forward biasing. So what do we say? Anode at higher positive potential compared to your cathode. So that is called as the forward biasing. So don't, if even for your students, you please send this concept. Don't tell them anode connected to positive, cathode connected to negative. Of course, it should be like that. But the criteria is my anode will be at a higher positive potential compared to that of my cathode. If that is the case, I call it as the forward bias of my diode. Clear? So now clear with this concept? Now we have given the bias to this. So what's going to happen now?
Electrons will start moving.
Electrons will start moving from where to where?
Anode to cathode.
Electrons will start moving from?
First, positive to anode.
No, electrons will start moving from where to where?
N to P.
Still there is a confusion. N to P. Okay, the electrons will start moving from your N to P, and in turn, what do we say? Holes start moving from P to N. Okay, you have it like this. This is electron negative. What do I have here? Negative plate of my battery. What happens to like poles?
Holes will get
What happens to the like poles? Fundamental. We have to go to the fundamental physics. Repel. They get repelled. So what will the negative of my battery do to the electron? It will repel it. It will repel my electron. So my electron will start moving from N to P. Same concept here. I have a positive plate of the battery. I have a positive hole. What will happen to it? It will be repelled. Right? So the electron, because there is a confusion now. Electron is going to move from P to N or N to P because there were varied statements. So be clear that this electron will be repelled. So as a result, electrons will move from N to P. Similarly, holes will move from P to N. So that is what is going to happen. So holes move from P to N. And your electrons will move from N to P basically. So I keep increasing the potential here, the bias here. So until say that barrier potential, which is say 0.7 volt or 0.3 volt for our silicon and germanium, what happens? There is no conduction. Once my voltage increases beyond that, then the conduction is going to start for the diode. Right? So electrons moves from N to P and your holes are going to move from P to N in this case. So how will be the characteristics? If I draw the forward characteristics, let's say I put this as forward voltage and then the forward current. So how will be the characteristics? Saturation. Why is saturation and all is coming into picture here? So I get a characteristics in this fashion. So this point is nothing but my, say, the 0.7 or 0.3. It's not cut off. Don't confuse with words. What is the voltage called as? It's basically the barrier potential here. In the characteristics, how do I call it as? Cut-in voltage or the threshold is for your FETs. Cut-in voltage or the knee voltage. Have you come across the term? You call it as the cut-in voltage or the knee voltage. There are so many terms which you get confused with. You are saying cut-off, you say threshold. Of course, they are all voltages, but it is for specific things, not here. So this is nothing but my cut-in voltage. Also, I call it as the knee voltage, right? So my current will be 0 till that point, and once the input is going to go beyond my barrier potential, then conduction is going to start. Now, what will be the range of this? It's not voltage, sorry. It should be in milliamps. Okay? It will be, the current will be in the range of milliampere. So this is basically your forward bias. So let's say while I'm doing it practically, you're not going to do the experiment here. You will be increasing your voltage, say in steps of 0.1, and then you will be checking what is going to be the current at every stage. Then you will plot the graph. You will get a graph in this fashion. Okay. So in the forward bias, what happens? My electrons from N moves towards P. Similarly, holes from P move towards the N. When my input is going to be more than the barrier potential, then the conduction is going to start up. So till that point, your current is 0, and after that, you will get an exponential curve in this fashion. It's not a linear curve, it's going to be an exponential curve. And diodes as such are called as exponential devices. Clear with this? Next, let's come to what is your reverse bias. So what do we do in the reverse bias? Anode to anode, what should I connect now? Negative. And to the cathode, positive. Okay. So now how do I term? Like how we termed for the forward bias. We told anode should be at a higher positive potential compared to cathode. That is what we termed it for the forward bias. Same way for the reverse bias. Cathode at higher positive potential. Okay. So your cathode at higher positive potential, or in turn you say anode is at a higher negative potential. So this is going to be your reverse bias. So now in the reverse bias, what's going to happen? What happens in your reverse bias?
Electrons.
The electrons, here it is going to be. What happens to the electrons here? Attracted. It's going to be attracted towards this. And what happens to the holes here? Attracted. Attracted, because they are going to be of opposite. Now, along with these are nothing but what we have shown in the diagrams are nothing but only the majority carriers. Along with the majority, what do we have? The minority carriers also. So, if I say for a p-type holes are majority, what will be the minority in the lattice? For a p-type, holes are majority. What are the minority carriers? Electrons. Similarly, for an n-type, electrons are the majority. What will be the minority? Holes will be the minority. Now I am applying a reverse bias in this fashion. So what's going to happen? This electron gets attracted towards this positive. The positive holes are getting attracted towards the negative. So what will happen to my depletion region as such? Widen. My depletion region will widen. So that is one concept that we have to understand. The depletion region will widen compared to what was earlier. The depletion region will widen in this fashion. So now this entire area, it's being occupied by the immobile ions. Then from where the current flows? The current flow is because of the minority carrier, which will be less in number. Okay, so the holes here and the electrons here, which are nothing but the minority, they contribute to the current, which we call it as the leakage currents. Okay, so in the reverse bias, what we have is the leakage current. I may be having a random hole here. I may be having a random electron here. So that moves and it contributes to what is called as your leakage current or the reverse current. Okay. When I'm increasing this potential to a very large extent, then what happens? This minority charge carrier, they undergo cumulative, they go collide with a nearby atom. That in turn will create the electron. So because of the cumulative multiplication of the charge carriers, I will get in the reverse direction a breakdown like this. Okay, if you can remember your characteristics, but this happens in a very large voltage. It will take a very large voltage for this to occur. So this is say my VR in volts and this is going to be my reverse current. This reverse current, it can be say a microampere or nanoampere, or it could be your picoampere also. A very less current. Less current, why? Because it is of the minority charge carrier. Minority means it is less in number, right? And the current is flowing because of the minority, so it is going to be having a magnitude of micro or say nano or pico. You can imagine the scale, how less the current is. And this breakdown is going to happen at a very large voltage. How the breakdown will happen? Because of the cumulative multiplication of your charge carrier. This electron here, if I say here, it is just getting attracted towards this. Similarly, the electron here is getting repelled. This electron will go and hit a nearby atom. When it hits a nearby atom, what happens? Another electron will be released. So in that way, there will be cumulative multiplication of the charge carriers. So because of those cumulative multiplication, your device will break down and you will have a rapid increase in the value of your, sorry, I have changed the scale. This should be voltage. Please correct it. This should be your voltage. And this should be your current. So this current is say micro or nano or your picoampere. So because of the cumulative multiplication of your charge carriers, the device breaks down and your current will increase rapidly. So this is going to happen in a reverse direction at a very high voltage. We can see the diode data sheets. From the data sheets, we will come to understand what is the reverse voltage. For example, for the 1N4007, which we are going to use here in our lab, it can be operated till say 1000 volts in order to make it break. Whereas in the laboratory, what is the maximum DC voltage that we have? What we used yesterday was hardly 32. Though the the template says it is 32, but what we were getting maximum was only 30 volts, 29 to 30. Okay, but this breaks down at say some thousands of volts or hundreds of volts. Right? We'll come to know when we read the data sheet. So that's why we say the diode, it is unidirectional. Unidirectional means it's going to allow current only in one direction. So it allows only in the forward direction and it blocks your current in the reverse direction. Clear? So that is nothing but your semiconductor diode. So we can compare it to a open switch and then the closed switch. If I say it's a forward bias condition, how do I make it? How do I show it? It can be considered as a closed switch. I can just connect both of them. If it is in the reverse bias, then it can be treated as a open switch like this. Right? So this will be in the reverse bias. So this is basically a unidirectional switch. Fine? So allows only in one direction, which is nothing but my forward bias. What is called as forward bias? My anode should be at a higher positive potential compared to that of my cathode. And let us get to this also. When I say it is like a closed switch, ideally what should be the resistance? 0. Those concepts should also go to your. Ideally the resistance should be 0. When I say it's an open switch, ideally what should be the resistance? Infinity. Okay? It should be infinite. Okay? Clear with this? So now here we are telling is the cut-in voltage. This we can tell it as the breakdown voltage, VBR. If you have any doubts, you get it cleared because diode is very important. Later on, we have transistors. Transistor is nothing but two diodes connected back to back. If you understand the working of the diode, then the working of the transistor becomes very simple. Any doubts? Even if you have anything stored in your mind? Nothing. Now I'll just show you in the manual there is an exercise on this PN junction. Okay, we are not going to do here now because it's a simple thing what you would have done in your classes also. So you can help your trainers to execute that. We will go to the application of the diode directly. Is it visible? So this is the experiment, characteristics of a PN junction diode, where we are going to use 1N4007 as the diode. Okay, and then of course a current limiting resistor, and these are the other components that are being required for it. If you look at the circuit, so if you take the symbol of your PN junction diode, anode, and then you have your cathode. So this characteristics and all that we saw. Now coming to the circuit, this is the circuit that you will be asking your students to do. Okay. So this is the circuit, and this is for the forward bias condition, where I have a regulated power supply. In series with that, I have a 100 ohm, which is nothing but a current limiting resistor, followed by a multimeter. Then I have the diode. The diode what we are going to use is 1N4007. Then across that is nothing but the voltmeter. So this diagram is basically for your forward bias. So this is for your forward bias condition, where I have this positive connected to the anode and negative of my battery connected to the cathode. So what will I do here? I will vary the RPS, that is the power supply what we saw yesterday, in steps of say 0.1, and then note down the current as well as the voltage. Tabulate it and plot it such that I will get this curve. Similarly, this diagram is for your reverse bias. So in the reverse bias, what have we done? The negative of the battery is provided to the anode and positive is given to the cathode. And here you have your resistor, which is nothing but the current limiting resistor. Same setup. You have your meters, the ammeter as well as the voltmeter. So what do? I vary the voltage here, say in steps of 1.5, then steps of 1, like that, and note down the respective voltage and then the current. Clear? But the breakdown will not happen, because for the breakdown to happen, it requires hundreds and thousands of volt. But the RPS what we have is only till 32. Okay, so breakdown, you cannot view the breakdown there, just you can note down the readings, that's it. The breakdown will never happen, because 500 volt or 1000 volt only the breakdown will happen. Clear? So this is one experiment which you will be making your students to do, the characteristics of the PN junction diode. So whatever we have studied before coming to this lab, the theory you should have done in your class, and then you should make them do this particular setup and make them to take the readings. Okay. This manual is shared with you? No. Okay. Now just for you to understand how it has been structured, after the circuit diagram will be the procedure. Then we will immediately give the tabular column with all the values, what you have to set, everything we would have given here. Okay, so this Vs is nothing but what I set in my power supply, and Vf is nothing but the voltmeter reading, and If is nothing but the ammeter reading. Similarly, for the reverse condition, Vs is nothing but what I set in the supply, say steps of 0, 1, 2, 3 like that. Vr is nothing but the voltmeter reading, and IR is nothing but my ammeter reading. So then you can ask your students to draw the graph, and all the procedure, everything, it's being provided here. Okay. And after this, there will be a set of assessment questions. Once they are done with the lab, there will be a set of assessment question which they have to answer, right? So if they are having the observation, of course, they'll be having an observation book. The student has to write the answers there. So these are all like referring to the data sheet or making them think and then give the answers, logical thinking like that. Nothing to do with the experiment what they have done. It will be like referring, if it is say a diode based experiment or a transistor based experiment, it will be referring to the data sheets and then writing down the values. Or if it is some experiment, then logically, if I change the resistor, what will happen? If I change the capacitor, what will happen? Like that, the logical thinking questions will be provided. So you can assess your students based on these things. So let's see first question. What is the maximum forward and reverse current of 1N4001? That is the question. Nobody will memorize that value. So what they have to do, refer. They should get the practice of referring to the data sheet and getting these values. Now you are also going to do that exercise. Have you referred data sheets before? Yes. Which all data sheets? Transistors. Good. Any other? No. So now you are also going to do that exercise and find out what will be the maximum forward current and the reverse current of 1N4007. Next, what is the operating temperature? The operating temperature will be provided there. Say I can operate till 75 degree, or I can operate say from minus 125 to say 250, like that the range of temperature will be given. So that also they have to note down and then write it. And what are the equivalent diodes of 1N4007? Say imagine I don't have 1N4007 with me. What could be the equivalent with which I can replace it? Okay, that if you search in the net, you will get the equivalent diodes. So that also has to be listed. Next, tabulate the maximum peak reverse voltage, RMS voltage and DC blocking voltage of this 4000 series. So you can use the data sheet and then you can write it. And I have given there only within brackets where all to use the data sheets. Next, what are the typical applications of this diode? See, I cannot use the same diode for all the purpose. This 4000 series diodes are rectifier diodes. If I want it for a fast switching operation, then I cannot use this 4000 series. I should go for another one, say 414-way-8 or something like that. Okay, so each diode has got its own application. Fine. So they should know I cannot use the same diode for all the purpose. For example, I have OA79. I have say BY127. I have 1N4001 to 4007 series. I have 1N4148. So there are plenty of diodes. The same diode I cannot use it for all the purpose. Each has got its own applications. Right. So this 4000 series are basically for rectification. We call them as rectifier diodes only. Generally, we term them as rectifier diodes. So that it will be specified in the data sheet. So they should know where to look in, right? They should know where to look in and then find out what its application is. Next, mention the package of 1N4007. I think you have done this course given by Shanbag sir. Did he introduce you to the packaging? Yes or no? Yes. So if you say the diodes, they have got a DO. DO means diode outline packages. And if it is a surface mount devices, SMD. Okay. So there is a number. Say I have DO35. I have DO41 or something. So what does DO35 stand for? What does DO41 stand for? All that they should be knowing. It is basically to do with the packaging. It could be with a plastic package or it will be with a glass package. Okay, so all those details are available in the data sheet itself with the package and what is the material with which it is made of. So mention the package of 1N4007. Next, tabulate few package of diodes and their temperature of operation. Right? As I told you, you can have a plastic package, you can have a glass package, and that DO itself, there could be many variants available. Okay, all that has to be listed. And representation of an ideal diode. A representation of an ideal diode will be, we just now discussed. Ideal diode, how do I represent? Just now we discussed about it. No, of course, it's a PN diode only. Representation of an ideal diode. All of them are semiconductor. Diode means it's a PN junction only. Before entering into this experiment only, we discussed. And I told you ideally the resistance in the forward bias, ideally the resistance in the reverse bias. Switch. That is the ideal condition where I can show it as a closed switch or a open switch. So the resistance will be either 0 or going to be infinity. Okay, so that will be the ideal conditions. Okay, so you can also answer these questions at the end of the day. I want you also to answer these questions. So you can take a note of it. And I will tell you how to refer your data sheet. Please take a note of this. How to refer your data sheet, I will tell you. Then you can give the answers for these questions. So lazy to write also. Just take a pic. If you write something only, at least the terms will go to your mind, right? So I was telling about the package, right? This is the glass package. Okay, I'll just circulate. And this is nothing but your plastic package of the diode. You can just... So underneath the assessment question only will be your assessment sheet also. You can give marks to your students immediately. You can give the marks. Okay, out of 10 for every experiment you can evaluate them. So we have given what are all the parameters you have to check. For example, here we have given usage of current equipment or components as per the bill of materials. Bill of materials means what we used to say as components or apparatus required. That is called as bill of materials here. So if they are using the correct components, like we did a mistake yesterday. Resistor we had taken it wrong. So our students are not supposed to do that. So take care of all those things. Then appropriate placement of the components on the breadboard. So as I was telling, they should follow that art of breadboarding. And the signal should flow from left to right. Okay, my input should be on the left side. I should be seeing my output on the right side. So from left to right it should be, not in the reverse or in a haphazard manner. Connections on the breadboard, correct circuit connection and flow of signal from left to right. That's very essential, right? If at all they are participating in say world skill competitions and all that, these are all some of the parameters that will be noted. So no haphazard connections. Always the signal should flow from left to right. Then conduction of the experiment following the given procedure, not on their own. Whatever procedure is given, stepwise they have to execute that. Next, accuracy in the measurements. So whether they are taking down the readings properly or not, all that has to be taken. Yesterday you were telling. It's not the case. Okay, so accuracy in reading is important. Next, usage of proper symbols and prefix in the circuit, tabulation and graph. So if it is a forward voltage, it should be written as VF only. If it is a diode voltage, it should be written as V suffix D. So they should use appropriate notations everywhere. Current means I and then within bracket should be its units, say ampere or milliampere, whatever. So proper notations and then their units. Then accurate calculation, interpretation of results from the graph. So here in this diode experiment, they would have drawn the graph. From the graph, they should be able to find out what is the cut-in voltage of the diode. It may not be 0.7. So I was specifically telling it's an ideal value. So practically what is it going to be? It may be say 0.56 or it may be 0.6, something like that. So that accurately from the graph, they should be able to find out what is the cut-in voltage. Next, equipment handling and tidy workplace. Okay, so how good they are in handling all your say power supply, the multimeter. In multimeter, they have to know where to set the knobs. If they are measuring the current, it should be in milliamperes or something, an appropriate range. If they are measuring the voltage, the DC voltage, and switching between the voltage and current probes, all that they should be used to. So you observe that and give marks for all. And finally, at the end of the day, when the experiments are over, the table should be neat and tidy. That's very important. So all those parameters we have listed. So experiment wise, it might change also the parameters, but on a scale of 10, you have to evaluate for a scale of 10 basically and give the marks. Clear? Now let me show you the data sheet and later on you can give the answers. So this is the data sheet of our 4000 series diodes. Is it visible? So 4000 series, so 4001 to 4007. All the diodes, their parameters are listed here. So whatever questions I have asked in the assessment, they will be able to take down the values from this data sheet itself. So now here only you can see it's a general purpose plastic rectifier. And down it specified DO41. So DO means it is diode outline package. And 41 is the specific number. So DO41, what does it signify? Similarly, we have other packages like DO35 or something. What does DO35 signify? I've asked a question, what are the other packages also? Okay, so all that they should be able to interpret from the data sheet of the device. Now you have a list of say 4000 series. In which way are they going to be different? They are going to be different based upon their parameter ratings here. Okay, you can see here the symbol means the notation for that particular parameter. 4001 till 4007 it is listed here. Okay, 4001 till 4007 all the parameters are listed. So whichever, for example, I say a maximum repetitive peak reverse voltage. So what should be the peak voltage beyond which the breakdown will occur for my diode? If I take 4001, it is at 50 volt. Whereas 4003, it is at 200 volt. Whereas when I use 4007, it is at 1000 volt. So that's what I was telling. You will not be able to observe the breakdown at all because it will take place at say hundreds or thousands of volt. Right? So this is my reverse voltage. Similarly, if I take my operative temperature, there was one question. What is operating temperature range? So this is basically from -50 to your 150 degrees Celsius. So all those details will be available in the data sheet. So you should also expose this to your students and then you should make them use the data sheet. And all the parameter will be visible here. And depending upon the experiment, what is required, that much is those values can be taken. So for us, only this much is required. Okay. And there was one question on, say, application. For what application it's being used. So typical application, it will be listed somewhere here. Yeah, typical application, it can be useful for general purpose rectification of power supplies, inverters, converters, and freewheeling diode applications. Okay. For switching and all, I have to go for the fast switching diodes basically. And if you see this entire data sheet, and here the polarity is also given, color band denotes the cathode end. So here you can see the symbol of it. This is the color band. So that band denotes it is the cathode end. So this is anode and this is going to be the cathode. I think the diode got circulated. So here you will be having the silver color ring. That's the cathode part. Opposite will be your anode part. So likewise, if you go for every diode with its specification and you go to the data sheet, you can get the complete details, right from the polarities to all the electrical as well as the mechanical parameters. So here you can see the primary characteristics being listed. Okay. And all other, these things are available. Forward voltage, say, forward current, maximum it is going to be 1 ampere. So till that I can safely use this particular diode. And if you see the junction temperature, as we saw, it is still maximum is 150 degrees Celsius. Package is being specified. This mechanical data, it is for your soldering purpose. How do I space it? What will be the distance between the leads? Width of it, length of it. All those mechanical data are also available. Okay, so that I can just show you. Okay, fine. So whatever questions you have noted down, no, you also go to the data sheet and note down whatever questions I have asked. So now we have learnt about basically diode, how it works, and what should be the respective experiment that has to be carried out by the student in the lab. Next is the application of this diode, application of this PN junction diode. So as part of that application, we are going to learn about the rectifiers. Okay, so rectifiers we will learn and then we will also do the experiment hands-on with that. So having learnt about PN junction, now the application of your PN junction diode is so one main is it can be used rectification. What are the other applications? What are the other applications that comes to your mind? Polarity protection. Then for your ESD, such that there will not be an immediate surge in current. Then you have learnt all these things. Clippers, clampers, yes. So clippers, clampers also make use of this PN junction diode only. So not only rectification, it can be useful for clipping, clamping, then for your protection. Okay, for all these, it has got n number of applications. Among this, what we are going to see now is about this rectification. Clear? So the circuit which does the process of rectification, it is called as a rectifier. So what is rectification basically? Converts
AC to DC. Pulsating DC.
AC to pulsating DC. Yesterday only I corrected that. Please don't say AC to DC. It is AC to pulsating DC. Okay. So rectification basically is AC to pulsating DC. That is the process of your rectification, and the circuit which does is nothing but your rectifier. Now, the application, what is that we are going to use here is a PN junction diode, a rectifier diode. That too, what we showed you now, which is 1N4007. That diode only we are going to use for the purpose. Now, this rectifier, it has got types. One is nothing but our half wave rectifier. Next is going to be our full wave rectifier. In the full wave rectifier, once again we have got center tapped and bridge rectifier. So what we are going to learn now is about this half wave rectifier. It's a simple circuit. Okay, we'll learn this half wave rectification now. So half wave rectifier in general written as HWR, half wave rectifier. So this is basically your circuit where I have a step down transformer. Are you able to understand? It's a step down or step up? How do you say it is step down? Winding ratio. So here I have given in the secondary side. This is the primary side. This is the secondary side of my transformer. In the secondary side I have given with less number of windings. So this is nothing but my step down transformer. Followed by the diode, and then I have the load resistor connected. Now first let's learn the working of this, and then we can see the respective circuit, the practical circuit. Now from the transformer, the input, the primary side, this is the primary side. This is your secondary side of your transformer, right? So to the primary, what is that? You have connected to your AC mains. That is 220 volts with a frequency of say 50 hertz. The transformer, what does it do? It steps down the voltage. So we have got two types. One is say 12 volt, another is 15 volt. So depends what you get. What is given to you? See, that's not transformer. See, this is your transformer. This is the transformer. Okay, the primary side, just two wires are there. Secondary side, there are three wires. So what is given to you is basically a center tap transformer. Okay, all these fundamentals, I think it's all covered in the previous classes. So it's nothing but a center tapped transformer. So now I have written it as 12 and 0. It depends on the specification, what is given to you. 12. So I think whichever has come in this box, it's 12. So 12 means it's 12, 0, 12. 12, the center is 0 and the other extreme is 12. So what it means is if I connect the extreme wire and the center wire, I'll be able to get 12 volt. Same way, this side also, right? So what is given to you is basically a 12 volt transformer, a center tap transformer. So in that only one half we are using. We are not using the both halves. We are just using only one half, 12 and then the 0, right? So this is the transformer followed by your diode, the diode with the plastic package, that is nothing but my 1N4007. The plastic package what you saw, that is nothing but your rectification diode. And then your load resistance. Load resistance, you can connect a resistor. Clear? Now how this is going to work? I provide a AC signal to it. So this is nothing but my input, an AC signal input given. So what is the value? It's 220 with a frequency of 50. Now at the secondary of the transformer, what will I have? 12 volt. Okay, what will be the frequency of the signal? 50 hertz. So I will have a step down value 12 volt for a frequency of say 50 hertz. Now this is given as an input to my 1N4007. That's my diode, right? So let's do it, say positive half cycle what happens, and for the negative half cycle what happens. Okay, so during the positive half cycle, so let me draw it once again. So I'm just giving the positive half. So I have 12, 0, just the positive half cycle is given. So what will be the polarities here? Plus and then a minus. So what happens to my diode basically? I have a plus and here it is minus. So what happens to my diode? Forward bias. My diode is forward biased. So as it is forward biased, what happens? Ideally, it is as good as a short circuit. So it is as good as a short circuit. So my current flows through my load resistance. Okay. So the current flows through my load resistance. What do I get as an output? I get positive half. Right? Now, clear with this? Now, during the negative, what happens? Next, I am giving this negative portion. So, what will be the polarity here? I have a minus, I have a plus. What will happen to the diode now? Reverse biased. If it is reverse biased, what happens? If it is reverse biased, open circuit. So, it is as good as a open circuit. Will there be any flow of current? No. So, I will have my, I will have my output to be 0. So, I will have the output as 0 over here. Now, this is say a continuous signal. Next, the next half cycle will come. So, the next half cycle, what happens? Closed. So, I'll have the diode here in the closed condition. So, current will flow through my load. So, I'll have this part. And during the negative half, once again, what happens? Open circuit. Goes open. So, it is going to be 0. So, in this way, for the sinusoidal input, what we have given, what are we getting at the output? We are getting one half cycle being rectified. Okay. So, here according to this circuit, which half cycle is rectified? Positive half cycle. And why do we, I was correcting your statement when you told rectification means converting AC to DC, I was correcting. Don't use DC, it should be pulsating DC. It is unidirectional. My output is unidirectional. It's only in one direction. Say only in the positive axis. But what's happening? A DC signal means it should be straight line like this. Okay, the frequency should be 0. But that is not the case in my output. There are some AC components present, which I call them as ripples. So those unwanted AC components are called nothing but my ripples. Okay. So this is nothing but your pulsating DC. This is your pulsating DC. So what does this do? It converts AC to a pulsating DC. So during the positive half cycle, it is acting like a short circuit. So I get the positive half here at the output. During the negative half cycle of my input, my diode is acting like a open circuit. So I get the output to be 0 and it repeats. Okay. Now the question is, will it work only for the positive half cycle? Is it going to work only for the positive half cycle? No. Negative. So what should be the change in your circuit? What should be the change in your circuit?
Both sides will have to taste it.
No, in this half-wave rectification itself, now as per this diagram, what it does, only the positive half cycle is getting rectified here. No, don't go till that. My question is very simple. Positive half cycle, I am getting at the output. Negative, it is open, so I get a 0. What if I want to rectify my negative half cycle? What should be the change in my circuit? Diode is reversed. That's it. Your diode should be reversed. Okay. Hope you got my question. Fine. So my diode should be reversed in this fashion. If I reverse it, what will I get at the output? Negative. It will continue like. Clear? So if your student by mistake has connected the diode in the reverse direction and you are looking for this waveform and you are telling no, it is wrong. No, it's not wrong. It is rectified only. But what he has done is he has interchanged the polarities of the diode as such. Okay. Because generally when they say rectification, it rectifies the positive half-wave rectification. If we ask, the general answer will be it rectifies the positive half cycle. No. It rectifies only one half cycle. Positive or negative, it depends upon the connection of my diode. If I connect it in this fashion, it is the positive half cycle. If I connect it in this fashion, it's going to be the negative half cycle. Clear? So till this is the concept clear for you? Okay.